limits at infinity is what we're looking at today. So keep in mind that infinity is not actually a number. It's boundless. It just means we're either increasing or decreasing without bound. But we still want to know when we have limits whether or not we're going to infinity or not. And because we know it, technically the limit doesn't exist. We've talked about that, but we still want to know where it's going. And so it describes a situation in which some numerical quantity gets larger and larger without bound, and similarly the same thing with negative infinity. So basically, if you have a limit at a number that approaches either positive or negative infinity, that tells us we have an asymptote on our graph. So if you look right here, we have, it looks like a vertical asymptote at x equals 1. This is x equals 3, and this is a vertical asymptote at x equals 5. So at 1, we can see both ends of our graph are going down towards negative infinity. So I would say the limit as x approaches 1 goes to negative infinity. And I can do the double-sided limit because both left and right side go down to negative infinity. Now, like I said, technically the limit doesn't exist, but we're going to be writing either positive or negative infinity to tell us that there's a vertical asymptote here. So at 3, both ends are going up towards positive infinity. So we would just put infinity since both the left and the right side are both approaching positive infinity. And at 5, we can see that the double-sided limit does not exist because and remember this is the right, when you have a plus there, and this is the left-sided limit. So this is the left side, this is the right side. You can see the left side is going up towards positive infinity, while the right side is going towards negative infinity. So therefore, the double-sided limit doesn't exist. So vertical asymptotes. The vertical line x equals c is a vertical asymptote of the graph of the function f if at least one of the following is true. So if we have the limits as you're approaching some number from the left side, the right side, or the double-sided, and goes to infinity or negative infinity. So given the graph of the piecewise function shown below, complete the following statements or state that the limit does not exist. So we're looking at first, it looks like the limit as x approaches negative infinity. So here, it's hard to tell, but looks like we're approaching an asymptote here at 0. So I would say 0. The limit as x approaches positive infinity, you can see is going down towards negative infinity. The limit as x approaches negative 2 from the left side would be approaching 2. And from the right side, we're approaching 3. So that means the double-sided limit does not exist. And then as we approach 2, that's a double-sided limit. So we want to look at the left side and the right side are both approaching the same value, which is a y value of 3. So maybe pause the video so you can do these on your own. When you're done, on pause, and we'll look at the solutions. So for A here, the limit as x approaches negative infinity. So as we're approaching negative infinity, it looks like we have an asymptote, horizontal asymptote or graph right here at 2. The limit as x approaches negative 3 from the right. Remember, this is the right side. So negative 3 from the right side would be right here in my graph. So it looks like we're approaching a y value of 2. 0 from both sides. So here's the left side's approaching negative 2 and the right side's approaching negative 2. So then the double-sided limit would be negative 2. Even though there's an open circle there, because remember, it doesn't have to necessarily equal 2. Or sorry, equal 0, I should say, because the y value is negative 2, but we're approaching an x value of 0. At negative 2 from the left side, so looking at negative 2 on my graph here, from the left side, remember this is the left, we can see, oh, no. Oh, sorry, not negative 2, positive 2. Okay, so say, I don't know, kind of hard to see that number, but 2 from the left. So here's a vertical asymptote at x equals 2. So this is the left side. So we're approaching positive infinity. If we did the limit as x approaches 2 from the right side, we would say for this function k of x would be negative infinity. K of 0 equals this closed circle here at 3. And limit as x approaches positive infinity. Looks like we have an asymptote at -1. So horizontal asymptotes. The line y equals L is a horizontal asymptote of the graph of the function of f if either the limit as x approaches infinity or negative infinity approaches some value. Then if it approaches some real number, such as L, we're saying in this case, that's how we know that it's going to be a horizontal asymptote. So remember, as you're getting that larger and larger x values in positive negative direction, that's how we know this is different than when we're approaching a number. So this one, keep in mind the vertical asymptotes, you're approaching some number such as c, but in horizontal asymptotes are approaching either plus or minus infinity for x. So let's recall some stuff about our asymptotes. When the numerator degree equals the denominator degree, then you can look at your leading coefficients. It's the ratio for the horizontal asymptote. So horizontal asymptote would be y equals 7/5. Here it would be, oh no, sorry, the degree of the numerator is less than the degree of the denominator. So here it's horizontal asymptote at y equals 0. And when the numerator degree is greater than the denominator degree, then we say there is no horizontal asymptote. We have a slant or other asymptote. And so this only works for rational functions, so keep that in mind. This is for rational functions and behavior. So if it's not a rational function, you can't use this to kind of help you out. You can use our polynomial in behavior, but you have to be careful in functions that are not. So we're going to evaluate the limits, and we're going to go ahead and also write I don't know. Yeah, we'll write the horizontal asymptote or other. Well, we'll just do it as we go. So here we can see we have a degree 1 over degree 1. This is a rational function. So therefore, it's the leading coefficient. So this is approaching 1. So that means that this has a horizontal asymptote at y equals 1. Now, another way you can do these is to use your calculator. So if I were to plug this into my calculator, I have x divided by parentheses x plus 9. And if I go to second graph, which is your table, second window, I'm on ask right now. So if you keep this on ask and keep this one on auto, go to second graph, which is your table. I'm going to delete these values out. Excuse me. So I'm looking at x values that are getting very large. So the larger and larger x values I plug in, you can see that our y value starts to approach 1. So it's just getting closer and closer to 1. So that's another way you can look at this graphically, but I always think it's a lot easier if you know the rules from our rational functions and it's a rational function, just to use that to help you. So looking here, we have degree 2 over degree 2. So this tells me there's a horizontal asymptote at y equals the ratio of the leading coefficient, so 3/4. So if I was to look at this on my calculator to confirm, if I go to my y equals, I'm going to plug in 3x squared plus 20 divided by 4x squared plus 9. Okay, graph. Here's the graph. So you can see it looks like it's approaching 3/4. Second window is already on ask, second graph. So as we approach larger and larger values of x, you can see that it says 0.75, so it's approaching 3/4. Just another way of looking at your graph. So over here we have degree 2 over degree 4. So that means this horizontal asymptote would be y equals 0 since the numerator degree is less than the denominator degree. And again, you could confirm this by plugging this into your y equals and look at very large values of x and see that it's going to 0. And looking at the next one, question number 4. So for this one, we have a rational function with degree 2 over degree 1. So for this one, I know that there is no horizontal asymptote, and the degree difference is a degree difference of 1. So I know there's going to be a slant asymptote. So you can find the slant asymptote by doing long division if you want, but you can also just think about it by dividing these first terms to see what your first term is going to be, because that's what really tells you what's happening on your graph. So if I divide 9x squared by 5x, because remember when you do your long division, you have 5x here, and you could even write 5x plus 0 if you want for the constant term. And then you would have 9x squared plus 0x minus 7. And so I know this is going to be equal to 9 over 5x, because x squared of x just becomes x. So that's what I'm concerned with, because remember, when you're looking at the end behavior, it's a polynomial function, so you can look at then your leading term. So every time you're using long division, when you're dividing those first terms, you're getting your lead term. So we would get 9/5 x, and then we would multiply each of these. So 9/5 x times 5x gives us 9x squared, and then times 0, which you don't need to write anything for. But and you notice that you cancel these out, bring down the 0, which you don't need to do, minus 7. And then in this case, you would have negative 7 over 5x. So you don't really need the rest of that. So this just tells us that this is just going to be your end behavior, because this would be the first term that we have. So we have no horizontal asymptote, and the end behavior of this function is odd, and the leading coefficient is positive. So the left end goes down and the right end goes up. So that tells me that as we're approaching positive infinity, we would go up towards positive infinity. If the question was to limit as x approaches negative infinity, your answer would be negative infinity. And again, you can go to your y equals and confirm this. So if we plug this into our y equals, parentheses 9x squared, oops, missed the x, parentheses 9x squared minus 7 divided by 5x. Again, make sure you put that in parentheses. Otherwise, it's going to think you're dividing by 5 and timesing that by x. So now if we go to our table and plug in very large values of x, so let's just say we plugged in 100, and then we plugged in 1,000. And then we just kept plugging in larger and larger values for x. You'll notice that means your y values are getting larger and larger, because that says 1.8 e to the 6. That means you're timesing that by 10 to the 6th power, which means you're moving your decimal place to the 6, to the right 6 times. So, and you can see the value down here when you actually click on that number using your arrows. It means it's just getting to be larger and larger, and not actually approaching a number. So you see now here we have 1.8 e to the 8. And if you hit your graph too, you can even see that slant, it's following your slant asymptote. So you can even see it's going up towards infinity. So the next one, we have a degree 5 over degree 4. So same idea with this one. We're just going to look at those lead terms to help us figure out what the lead term would be. So we know there's no horizontal asymptote. There's a slant asymptote because the degree difference is a degree difference of 1. So 2x to the 5th over 8x to the 4th gives us 1/4 x. So this is, again, odd positive. So the left end is going down, the right end is going up. So that tells us this is going towards positive infinity. And of course, you could also plug that into your calculator to confirm. Now, the next one is not a rational function. So again, if you want to use your calculator, so we can plug this in. We have the square root of 9x to the 4th power plus 3x and then plus 2 divided by 4x to the 3rd plus 1. So if I hit graph, here's what my graph looks like. So as we're getting closer and closer to infinity, it looks like we're approaching 0. So second graph. So here you can see that the larger and larger values I'm plugging in, now it says e to the negative 4th. So that's times 10 to the negative 4th. and this becomes negative times 10 to the negative 5, negative 6, negative 7. So that means we're just getting a like 0.0000, so it'd be 8 zeros and then 7, 5. So that means this is just approaching 0. So remember, sometimes your calculator just can't write that number because it's just trying to calculate too much. So here, another way to think about this, is, again, if you look at your first terms here, the square root of 9x to the 4th over 4x cubed gives us this in the numerator, that would be 3x squared over 4x cubed. So the degree of the numerator here is 2 over degree 3, which means we have a horizontal asymptote y equals 0. But again, just use your calculator to kind of help you look at that. So next we're looking at what are we called power functions. So note it has a number in front and x to some power. These are called power functions here. You can think about them like a polynomial function with just one term. So when we're computing these limits, again, you just need to think about your polynomial end behavior. So we have odd positive, odd negative, even positive, and even negative. So odd positive, left end's down, right end's up. Odd negative, the left end's up, right end's down. Even positive, both ends go up. Even negative, both ends go down. So for this one here, we can see that this is an odd degree and the leading coefficient is negative. So this is odd negative. So odd negative means that as we approach positive infinity, the right end goes down, and negative infinity, the right end goes up. So this, sorry, should be negative infinity here. And this would be positive infinity. Positive infinity. For the next one, we have 1/3 x to the 8th power. So this is even positive for both these. So it means both ends go towards positive infinity. As x approaches infinity, y goes to infinity. And as x approaches negative infinity, y values go to positive infinity for both of those. For the next one, we have odd power. So this is odd positive. So as we approach positive infinity, our right end goes up and negative infinity goes towards negative infinity. And then the last one, we have an even degree with a negative leading coefficient, -7. So both ends go towards negative infinity. Looking at the next ones, same thing here. We have a power. No, this is a rational function. So this is, remember when the degree is not there, it's degree 0, degree 5. So that means this approaches a horizontal asymptote at y equals 0. So this approaches 0 and 0. You can confirm that with your calculator as well. Here, you can actually, when you're looking at limits that have more than one term, you could look at each of the terms separately. So this is 5x, which is odd degree and positive. So that means that the left end goes down, right end goes up. So this is going towards infinity. And here we have -2 over x plus 3 is a rational function. So this is degree 0, degree 1. So this is approaching 0. So infinity minus 0 would just be infinity. So I know this is going to infinity. But let's get out our calculator. So if we plug this into our calculator, we have 5x minus 2 divided by x plus 3. Make sure you put that x plus 3 in parentheses. And then if we go to our graph, we can look at our graph, the second table, and we're plugging in larger and larger values. So you can see that the larger and larger your values get, the larger and larger the number gets. So we're going to infinity. So then if we did the same for a very large negative value, it looks like we're going towards negative infinity, which makes sense because if you plug a negative value in here for this x, it's going to make it a negative number. Looking at the next one, it's a rational function. So we have degree 5 or degree 2, which tells me there's no horizontal asymptote. So if we think about negative 3x to the 5th over x squared, our lead term would be negative 3x to the 3rd, which is odd negative. So the left end goes up, right end goes down. So this would be going towards negative infinity, and this would be going towards positive infinity. And again, when you look at your graphing calculator, the larger and larger numbers you plug in, you'll notice that you're either going towards a larger and larger negative number for the first one for E, and for F, you would be approaching a larger and larger positive number, so towards infinity. And that is it for the lesson.